will discuss about the linear phase filter. Okay, a filter is said to have a linear or non-linear phase, and this non-linear and linear functionality depend upon one function known as delay function. Okay, so in this delay function there are two types. One is phase delay and group delay. Okay, so here what we are going to see is this filter. A filter is said to be a linear when phase delay and group delay values are constant. If both the values are constant, then the filter is said to be a linear phase filter. Understood? Okay, so when the filter is said to be a linear phase filter, when it has a constant phase delay and the group delay. If the phase delay and group delay are not constant, then it is said to be a non-linear phase filter. Okay, so here now we are going to discuss only about the linear phase filter. Okay, so here the another name for the linear phase filter is known as constant time delay filter. Okay, now we'll see what are all the constraints required to have a constant phase delay and group delay. So in order to have a constant phase delay and group delay, it should satisfy the condition that summation n is equal to 0 to m minus 1 h of n sin omega tau minus omega n equal to 0. Okay, so in order to have a constant phase delay and group delay, it should satisfy this requirement. So now we will see how we will obtain this relation. Now we know that the frequency response of the filter can be written as h of e power j omega summation is equal to 0 to m minus 1 h of n e power minus j omega n. Now we are going to have some derivations, and from that we are going to prove the thing what I have told. Now this I am going to prove here. Okay, now I am going to have some derivations and I am going to prove that thing. Okay, now we know that e power minus j omega n can be represented as that is cos omega n minus j sin omega n. Okay, now what I am going to do is I am going to expand this functionality, and from that I am going to find out the magnitude and phase response. Okay, so we know that this h of e power j omega magnitude, how will you write this is that is real part the whole square. So real part is summation n is equal to 0 to m minus 1 h of n cos omega n the whole square plus summation n is equal to 0 to n minus 1 h of n sin omega n. Okay, sin omega n the whole square. So this is the magnitude part. Now here we are not going to concentrate on this magnitude part. Here in order to have a linear phase, we are going to concentrate on the only phase part. So here this can be represented as tan inverse of imaginary part by real part. The imaginary part is 0 to m minus 1 h of n sin omega n, and by divided by summation n is equal to 0 to m minus 1 h of n cos omega n. So this is what the phase value I am obtaining from this equation. Okay, next one, we know that tau is equal to minus phi of omega by omega. That is, this is from the phase delay relation. That is, see here, this is from the phase delay relation. Now I am choosing this minus phi of omega by omega, and I am going to equate. So consider this equation 1 and consider this as equation 2. I am going to equate equation 1 and 2. So the cross multiply it. I need only phi of omega. So minus tau of omega is equal to tan inverse of minus summation n is equal to 0 to n minus 1 h of n sin omega n divided by summation n is equal to 0 to m minus 1 h of n cos omega n, right? So tan inverse of minus theta is minus theta. So tau omega can be represented as tan inverse of the same thing, you will get it. Okay, taking tan inverse this side. Okay, so tan of tau omega is equal to, so summation n is equal to 0 to m minus 1 h of n sin omega n divided by summation n is equal to 0 to m minus 1 h of n cos omega n. Now we know that tan can be written tan we can write it as sin theta, tan theta by is equal to sin theta by cos theta. Now see here I have this equation. I am going to simplify expand this one. So tan sin omega tau by cos omega tau, then I have written the same, then I am cross multiplying it, this two side will go here, and when I bring this to the one side, okay, when I bring this to the one side, this equation is similar to sin A cos B minus cos A sin B equation. So I am this is h of n is common, so summation n is equal to 0 to m minus 1 h of n sin omega tau minus omega n is equal to 0. So we have proved this one right now. Okay, so in order to have a in order to have a linear phase, the phase delay and group delay should be constant. In order to have a constant phase delay and group delay, this condition should be satisfied. Okay, so this is what the thing we have proved now. Now here there is some relation you need to know. This is tau is equal to m minus 1 by 2. This tau can be this delay can be obtained from the m minus 1 by 2 equal relation. And also here there are two types of filtering concept we will see. One is symmetric filter and another one is anti-symmetric filter. Okay, so in this symmetric filter, what the design is here, the coefficient obtained this side is similar to this side, and in anti-symmetric filter it is just the opposite, right? You remember what is anti-symmetric and anti-symmetric filter concept. That is, in symmetric concept, h of n is equal to h of m minus 1 minus n, and here h of n is equal to minus h of 1 minus 1 minus n, which is the meaning that there is one center coefficient. The coefficient here is both are similar. In antisymmetric, these coefficients are suppose considered here the coefficient is 2, here you will have minus 2, like that it will an antisymmetric response. So here this is what the representing this symmetric and antisymmetric. We will see in detail. Now we will see all these derivations in detail now.